All right. Chapter 21. In Chapter 20, we discussed port fuel injection. So port fuel injection, we're spraying fuel at the backside of an intake valve during the intake valves, when the intake valve opens during the intake stroke. Direct fuel injection is a little bit different. Direct fuel injection does not require the intake valve to be open because direct fuel injection is spraying fuel directly into the cylinder. So up until like the last 10 years, manufacturers never incorporated a fuel injector in the cylinder. They always sprayed fuel somewhere in the intake airstream itself. Diesel engines have been using this technology since the beginning of time. Diesel engines rely on fuel igniting off of the heat from the compression. There's no spark plug. And so diesel engines can only spray fuel when we're ready for a combustion event. Manufacturers have gone to direct fuel injection on gasoline engines primarily because of demands for fuel economy and emission standards. So direct injection allows for better fuel economy, it allows for cleaner tailpipe emissions, and it also allows for higher performance. It comes at a cost, though. It's a very expensive system. So manufacturers probably wouldn't have incorporated this technology on their cars unless the federal government pushed them to do so. It costs them more to develop these systems, it costs them more to install them on cars, thus it drives the cost of the car's overall price up, making them less competitive. Repair costs are high. Warranty, under warranty, manufacturers have to pay for these components. So there's really no other driving force other than emission standards and fuel economy standards. So port fuel injection would spray fuel with the incoming airstream. So up until this point, fuel was never sprayed independently of like the 4-stroke cycle. So the only time fuel would come into the cylinder is when the intake valve was opened, whether it was a carbureted vehicle or port fuel. Direct injection allows for an infinitely timed control delivery of fuel. You can spray fuel really at any point because we're no longer relying upon an intake valve to open to allow the fuel to come into the cylinder. We can spray the fuel at any given point of piston travel, independent of intake valves opening. So if we look at engine tech and how it's advanced over time, variable valve timing allows manufacturers to kind of control the amount of oxygen that is allowed into a cylinder. And what that does is it allows manufacturers to control like compression ratios, for example. If we open the valve later in the intake stroke, when the piston's further down its travel, we can get less oxygen. If we open it a little bit before top dead center, before the piston starts to move down, we can get more oxygen into the cylinder. We could achieve a higher volumetric efficiency, which allows for more power, or we can reduce the volumetric efficiency and reduce power. Remember that horsepower equates directly to gasoline consumed. So if a manufacturer is trying to lean out the engine, detune the engine to gain fuel mileage on the highway, they can simply change the timing of the intake valve and reduce the amount of oxygen that comes in and kind of detune the engine. But there's an issue with port fuel and variable valve timing. And that issue is we still need to get the fuel into the cylinder. And so we can only retard the timing so much of our valve train before we don't have enough time at all for fuel to be delivered. So if you think about it, a port fuel injector, it has to spray with the incoming air charge. And so if we reduce the amount of time that valve is open, we actually start to limit the amount of fuel that can also be sprayed in. And so we reach a plateau, a certain point where performance gains can only get so far before we are limited by mechanical operations. And so direct fuel injection completely eliminates that problem. By putting the injector in the cylinder, we can now spray fuel at any given point, and so the fuel delivery is no longer relying upon valve train timing. Therefore, we can detune that cylinder even more. We can also run higher compression ratios. Think about one of the issues with fuel and volatility. Gasoline entering a cylinder during the intake stroke it's there. So as we start to squeeze that air and make that compression ratio tighter and tighter and tighter, we start to develop heat. And so we run into an issue with port fuel engines that it's called like pre-ignition. So as we're squeezing that air, there's also fuel in it. And so that fuel gets to a point where it flashes off, potentially, with too much compression. So if we put the injector in the cylinder head and spray directly into the combustion chamber, we can keep the fuel off and out of that air charge until we actually want the combustion event to take place. Does that make sense? So the timing is probably the most critical component of this. We are no longer relying on the normal 4-stroke cycle. That's not a limiting factor anymore. Also, take a look at the top of the piston in this illustration. Manufacturers in the past, for your gasoline engines, would utilize a flat top piston. Maybe it was slightly dished, maybe it was slightly domed, but the combustion chamber in previous port fuel, carbureted, etc. engines, the combustion chamber was in the cylinder head, 100%. So if you think back to engines 110, when you took the cylinder heads off and you flipped them over, you could see the valves. The head had a little dish to it, and that's the combustion chamber. Manufacturers are now incorporating some of the combustion chamber in the piston itself. And so there's multiple reasons why manufacturers do this, and it kind of just depends on the engine that they're designing and what the end goal is. So the top of the piston, maybe the shape of the piston may be to aid in the swirl effect, to help atomize the air and fuel. It might also be there to kind of offer a few different modes of operation. So if you think about a piston starting at bottom dead center, you have that entire cylinder's displacement that you can make power out of. If we open that valve in the very beginning of the intake stroke, we can fill that entire volume, the entire chamber with oxygen. But if we open the valve late in the intake stroke, we could bring just a little bit of oxygen. And as we squeeze that oxygen up to the top of the cylinder, we can now actually turn that big cylinder into a small cylinder, because all that oxygen is forced into this top little portion. We could spray a lesser amount of fuel, still achieving stoichiometric air-fuel ratio, but producing way less power. So we can kind of set up several modes, like several displacements out of a normal engine. We can have an engine that maybe has 1 liter, and then we fraction it down to 1/10 of a liter. That allows for a leaner cruise down the highway without the leaner part. It allows for a power reduction without compromising tailpipe emissions. So that in and of itself is a great option with direct injection. Port fuel injection can never achieve this, because if we wanted to put less oxygen in, we'd have to spray less fuel, but we reach a point where our efficiency drops off, and now we start to run too rich or too lean, and we start to elevate certain tailpipe emissions because we can no longer achieve that stoichiometric air-fuel ratio. But by spraying fuel at the last second with a domed or a dished piston, we can, in effect, reduce the displacement of that cylinder and run a much, much lower horsepower mode, consuming way less fuel, but not sacrificing tailpipe emissions. Make sense? All right, let's move on to the next slide. If I can, there we go. So direct fuel injection systems add a few components. They add a high pressure pump and they add high pressure fuel injectors. But the rest of the system looks pretty much the same as your port fuel injection setup. So we still have a fuel tank, obviously. We still have a fuel pump. We have a fuel level indicator, a float of some kind. We have a sock, that's a pre-filter. We have a fuel pump module controlling the speed of the pump. These are pulse width modulated. We have a computer system that's controlling the speed of the pump. The fuel pump may be called a lift pump on these direct injection systems, or they may simply call it a low pressure pump. But if we look up here, we see the high pressure pump incorporated into the system. On the next slide, you're going to see a little bit more information on the next few slides on how this high pressure pump works. All of your low pressure pumps are electric. So we have power coming into an electric motor that is spinning a mechanical pump, right? So we're using electricity to create the lift pressure. The lift pump, the low pressure pump, is simply delivering fuel to the high pressure pump. The high pressure pump is mechanically driven. There are no electric high pressure pumps that I'm aware of on the market. We're taking 50 or 60 PSI and we're stepping it up into several thousand PSI. Every manufacturer has a different, I guess, pressure output. Most of these gasoline direct engines are running under the 5,000 PSI range. In diesel land, these high pressure injection pumps can achieve 25,000 PSI. So think about the energy that it takes in order to squeeze fuel to that rate of a pressure. An electric pump would have to be massive in size in order to step pressure up and keep the volume consistent. So manufacturers are using cam-driven injection pumps, meaning that the cam itself either has a gear or a lobe that mechanically actuates the injection pump. So in this slide, we can see a 3-lobed camshaft. So the lobe on a camshaft is an extra lobe, right? So the other lobes are still there to open and close the valves, but we add an extra lobe, and that lobe simply rocks on a plunger. So we're using mechanical energy of the engine to push on a plunger that compresses the fuel. So we're squeezing that fuel with engine power. It's really no different than like using an engine to run the oil pump or using the engine's power to run the alternator. We're harnessing some of that engine's horsepower to step up the fuel pressure. Now, that does cause a parasitic draw. It does take horsepower. We're using some horsepower, but we're exceeding that loss and parasitic draw with the benefit of having the higher pressure. All direct injected engines on cars are utilizing common rail. Now, what common rail is, the simplest way to put it is common rail just means that the fuel rail feeding fuel to the injectors is at a common pressure, and it's always charged, meaning that it's always under pressure. If you look back at old diesel engines, older diesel engines that were non-computer controlled incorporated what was called mechanical injection. Now, mechanical injection kind of operated on the distributor theory, where we have a mechanical clock that's rotating and an individual fuel line leaving the pump going to each individual injector. So as the head of the pump rotated and lined up with one of those hoses or those fuel lines, it would spray fuel to that injector in time. And as soon as the fuel injector sprayed its fuel, that line was discharged. Excuse me. So the fuel lines were only under pressure when it was their turn to spray fuel. Common rail charges the entire fuel system all the way up to the backside of every injector equally and all the time. Common rail technology is actually used on port fuel injection, but port fuel injection is at a much lower pressure. So it's not called common rail, but it really is common rail. If you look at a port fuel injected engine in some of those illustrations in chapter 20, you can see the fuel rail connect to each injector, but that fuel rail is under common pressure. So common rail is filling the backside of these injectors with several thousand psi of pressure, and then the injector itself is controlled electronically. So a computer is supplying positive and negative voltage to the injector coil when it's time for that injector to spray. Again, it's the same technology as port fuel injection. So we have a magnetic field that's created, the injector lifts off its seat, and the fuel pressure that's in the rail is allowed to pass through the injector and fire directly into the combustion chamber. All of these systems need to have pressure feedback. So you see fuel pressure sensors on all of these direct injected engines. The computer needs to be able to self-check as it commands fuel pressure up and down. So fuel pressure is not consistent on direct injection like it is on port fuel. Port fuel kind of hovers around the same pressure. It might fluctuate a little bit. 50 to 60 psi maybe is its operating range on port fuel. Direct injection is going to sweep a much, much broader range in pressure. Under light load, when not a lot of fuel is needed, you might have pressures that run as low as 500 psi. Under heavy load, when more fuel is needed, these injection pumps ramp up in pressure. Now they do that for two reasons. One is to get more fuel into the cylinder, and the other is to overcome the combustion pressures, the compression inside the cylinder. So think about why you need such high pressure. If you have a cylinder that is squeezing the air to 200 psi, you must have an injector spraying at multiple times higher pressures than that in order to have the fuel actually come out of the injector and not have the fuel get pushed backwards through the system. Okay, so another benefit of that high pressure, though, is better atomization. If you think about how much pressure is behind that fuel, you have an instantaneous atomization effect. When we open that injector and we push fuel through it at 2,000 or 3,000 psi, that fuel is instantly vaporized. So it's a much more efficient delivery of fuel as well, because port fuel under 60 psi, it's atomizing, but it's not atomizing in a fog. You still have droplets on a microscopic level. Direct injection basically eliminates that problem. It's spraying fuel out so violently that it's instantly fogging that fuel. So in the next couple slides, we have some illustrations of how manufacturers will change up the location of the injectors based off of what the design plans are. So the injector can be placed at the very center of the cylinder head, in the middle of the cylinder. It could also be placed off to the side. If we go back and forth between these two illustrations, you'll see the piston actually changes as well. So in this first example, we have a piston that is dished in the middle. So my example of reducing engine performance by decreasing, offering a different mode, so maybe two modes of overall like volume, like liter output size of that cylinder, we can have two modes in this example. We can have an engine that operates with the full size of the cylinder, and we could also have an engine that operates with just that top portion of the piston. So we can have an air-fuel ratio that's stoichiometric, but have a lower output in performance. In this example, we have a piston that is shaped to help incorporate the swirl effect. And you'll notice how you have to look at pistons maybe in 3D to really experience this. You can Google some of these images, but The piston shape is going to allow for, as the piston moves up and it starts to cause a swirl effect, that fuel injector is spraying fuel at a precise moment where that airflow is in a vortex that is like most ideal. So we're fine-tuning the delivery of the fuel. So we're not just spraying fuel into the cylinder and then later in the compression stroke swirling the air. We're swirling the air and then spraying the fuel, if that makes any sense. It aids in fuel atomization. Some manufacturers operate with 2 fuel injectors per cylinders. Toyota is an example. I think the book talks about Lexus. Toyota and Lexus are the same company. Some manufacturers utilize port fuel injection and direct injection. And you might wonder why they do this. And so there's some drawbacks to direct injection. The main drawback really is carbon. So I have a few slides, and I'm going to expand upon the text here a little bit. The textbook talks about some of the carbon issues, but before we get into that, let's talk about placing an injector in the cylinder and also placing one in the intake port using both technologies. So if you look at this illustration here, under certain modes of operation, port fuel injection does a better job than direct injection. So if we're trying to completely fill the cylinder, for example, if we spray that fuel with the incoming airstream, we might do a better job at atomizing the fuel in that particular scenario. But if we're trying to build higher power, we might want to spray not only just the port fuel, but also direct injection at the same time, because then we might be able to create a cooler combustion event and reduce those NOx emissions that might be present in that high compression ratio engine. So let's get into the carbon issues. The number one issue you're going to run into, and this is the reason why I'm not a big fan of direct injected engines. If you have a direct injected engine that is simply direct injection, it does not use port fuel injectors at all in the system, carbon is going to be your worst enemy. Carboning of the backside of the intake valves is caused by the PCV system. So to not go off in left field here, I'm going to take a minute and try to explain this so we don't get lost and confused. Here's a picture of carbon, right? So that's a direct injected engine's intake valve, that nasty carbon. We'll come back to that slide in a second. How does that carbon form? All engines by design have blow-by. The rings on a piston cannot 100% seal that piston to the cylinder walls. So some of that combustion goes past the rings and ends up in the crankcase. In addition to that, oil in the crankcase has a flash point where it actually vaporizes. It's one of the reasons engines will deplete their oil level over time. It's also an issue why running synthetics to 10,000 miles may not be the best option. Because over time, by design, engines will actually consume some of their oil. Some of that oil is left on the cylinder walls and gets burnt off. Some of it gets flashed off and ends up being burnt through the PCV system. So in the past, before we cared about evaporative emissions and tailpipe emissions, etc., manufacturers would vent that crankcase pressure into the atmosphere. Well, we can't allow those gases to escape because they're hydrocarbons. And so what manufacturers developed to combat those evaporative emissions is they allowed for the PCV system, so positive crankcase ventilation would allow those gases to be drawn back into the intake manifold. So if you think about it, those gases are not oxygen, they're actually hydrocarbon-rich vapors that are moving through the system. And so port fuel sprayed fuel on the backside of the valve. And it was an unintended benefit, but port fuel, by spraying fuel on the backside of the valve, we actually cleaned the carbon off the valve with the gasoline. So every time the gasoline was sprayed, that gasoline was washing the carbon off the backside of the valve. When we took the injector and put it in the cylinder, we created a problem. We got rid of the washing effect that the fuel was having on the backside of the valve. And so over time, 25, 30, 40, depends on the engine, but thousands of miles, after time has passed, carbon deposits start to form. If you think about what's happening here, we're actually decreasing the volumetric efficiency of that valve. That valve is becoming a restriction because carbon is building up. So as the carbon builds up, less and less air can actually flow into the cylinder. And so your customers are going to bring cars to you with not very many miles on them with drivability issues. You're going to be cleaning lots of valves on these engines as a technician. There are cleaning procedures. I have a video on walnut blasting as an example. So every 30,000 miles, maybe, you're going to have customers that develop misfires. You're going to have customers that develop poor fuel economy, maybe check engine lights on. It could get as bad. It could get to the point where you actually lose compression in the cylinder. If that carbon starts to make its way around the other side of the valve, it'll hold the valve open, and you can lose compression entirely in a cylinder. If it gets bad enough, you can have an engine that won't even start, or it won't run unless you hold the pedal all the way to the floor. So the process of cleaning this can be labor intense. You don't have to remove the cylinder head, but you have to remove the intake manifold. And so the intake manifold is taken off, and you mechanically remove the carbon. So watch the videos on carbon cleaning. There's a few different methods out there, but most people, even in dealerships, they're using walnut blasting. And there's been all kinds of aftermarket specialty walnut blasting machines. They're basically like sand blasters. You can make your own. You can go to Harbor Freight and buy just a portable sandblasting setup and use a shop vac. You don't have to spend big money on tools for this, but you're going to run into these issues as a tech. So the process of cleaning can cost as much as $1,000, depending on how invasive it is of a process to remove the intake manifold. You can use a borescope down the intake. So open the throttle plate and use a camera to actually inspect to see whether or not carbon is the issue. But the real problem here is this problem is going to keep coming back. So even if you have a customer that you repair this problem for, in about that same amount of mileage, if they don't change anything, like driving style, for example, or oil or fuel quality, they're going to be right back again needing this service. So it's becoming a costly issue. When the engines are brand new, the manufacturers, they're passing their EPA test and they're providing, improved fuel economy and improved emission standards for these engines. But look at this valve. What's going to happen after 20,000 miles? That engine's actually going to be performing less and less, and these emission tailpipe ratings that were set out at the factory are no longer going to be accurate. And so the fuel economy starts to suffer on these engines. The horsepower and performance starts to suffer. There are dyno tests you can research out there where after 20 or 30,000 miles, the stated dyno horsepower of an engine is decreased by 50%. So be aware of this issue. This is not new. If you've been in the auto industry for a while, you know of this problem. Everybody you work with is going to be aware of this. But if you're a consumer, I don't know. I don't think I want to own a vehicle that has direct fuel injection because of this issue. You have to kind of weigh out the benefit. If you're getting 300 horsepower out of a 2-liter engine and 50 miles per gallon, maybe it's worth it. Maybe it's not, So continuing on, how do we prevent that problem, right? So your customer is going to be bringing cars into your shop with carbon issues, and you're going to have to you're going to have to quote them, a fair amount of money to fix it, but you should probably let them know that that problem is going to come back in about the same amount of time unless you take some preventative measures. So manufacturers are actually starting to do this from the factory. They're installing these PCV catch cans. And what these catch cans do is they go in line with the positive crankcase ventilation, tube, and they act as a scrubber and a catch for those hydrocarbons. You can install these in the aftermarket world. You can put these on any car. It doesn't matter, but you want to make sure if you're going to do this as an option that you pick a catch can that is of good quality, and that's not going to come cheap. You're going to probably spend $300 or more on a catch can, but if you weigh that with the cost of cleaning these valves off every 30 or 40,000 miles at $1,000, you might be able to convince your customer into buying this. Now, this is going to prolong, it's not going to prevent, so keep that in mind. You're not going to end up never having to clean the valves again, but you should be able to delay how quickly that carbon builds up if we can reduce the amount of hydrocarbons that come back through the PCV system. We want the pressurized gases to make its way out, but we don't want the vapors that are containing gasoline and oil to make it through. And so these catch cans will separate and allow the liquids to drop out. Now you have to drain these, so you have to be aware of the systems on the car. So maybe every oil change, you have to open this thing up and dump out the little bit that it catches. But this is a viable option. Manufacturers are putting these on newer vehicles. So you might actually see this as a maintenance procedure. That's why I added this to the chapter. The chapter didn't really talk about this, but from the factory, you're seeing manufacturers put these on, and it's becoming a maintenance item. So there's an interval for when you have to open these things up and drain them and clean them out. There's no filter in them, but you still have to wash them out, dump the oil, and clean them up and put them back together. Another thing you can do and suggest for your customer on these direct injected engines is you can offer maybe an improved oil. So while changing the oil, and manufacturers are doing this anyway, they're suggesting, synthetic oils, true synthetics, not these blended 50% or, partially synthetic. You need a good quality synthetic oil in direct injected cars. A good synthetic oil is going to have a lower volatility rating or a score. You can look that stuff up on the internet. I'm not going to pick a certain brand for you, but you could probably take a guess at which oils are going to meet those requirements. They're the more expensive oil brands. The oil itself, by changing to a higher quality synthetic oil versus like a conventional oil, by being cheap, running like $2 a quart oil versus $10 a quart oil, you can actually reduce the amount of vaporizing that takes place with that oil. So a higher quality synthetic oil is going to vaporize less, meaning that less of the oil in the crankcase is going to pass through the PCV system, which is also going to reduce the amount of carbon that builds up. Another option is the Italian tune-up. Believe it or not, manufacturers are actually recommending a spirited test drive. It's in the literature. It says spirited test drive. Take the vehicle out and romp on it. If you've got a customer, I don't want to stereotype here, but you're little old grandpa type driver. They don't ever get the engine hot. They just cruise it to the grocery store, go to church or whatever, and come back, and they only get the vehicle running for 5 minutes at a time. That is going to negatively affect the carbon buildup. So you might recommend to the customer after cleaning their valves, we'll put maybe a catch can on. We'll switch over to a higher quality oil to help prevent this. But you need to also let them know, don't be afraid of doing a wide open throttle once a day. It's not going to hurt the engine. It's not going to blow anything up, but it's actually going to help get some heat and air velocity. That's the key part there, is heat, getting the valves hot, and getting lots of air charge moving through the intake that'll help blow off some of those chunks of carbon. So if you own a direct injected car, you have permission to romp on it once a day. Keep the carbon out of it. That also, the Italian tune-up also helps with keeping the injectors in the combustion chamber from carboning up. By getting the cylinder nice and hot and getting lots of compression and heat in that cylinder, it helps blow the blow the carbon off the tips of the injectors, because that's the other issue with direct injection. The tips of the injectors are in the combustion chamber. And if you think about it, the injector has a spray pattern that's developed by the little tiny microscopic holes on the end of the injector. And if carbon starts to deposit on those, you end up with an inefficient spray pattern. And so you kind of reduce performance of that injector because it's not atomizing fuel as efficiently. And so the Italian tune-up spirited driving does two things. It helps keep carbon off the intake valves, but it also helps blow carbon off the injector itself. So maintenance issues are probably like the biggest issue with direct injection. Direct injection is good for fuel economy. It's good for tailpipe emissions. It helps manufacturers achieve those strict standards that the federal government keeps upping. But it comes at a cost. The fuel injectors are expensive. Maintenance is expensive. When components fail, it's expensive to replace them. Testing procedures are also the other thing I need to talk about here. When you have let me go back to the diagram here. When you remove fuel injectors on the high pressure side, you need to be very, very, very careful that that system is not pressurized. If you have a couple thousand PSI of pressure in there and it's not bled off, you can hurt yourself with 2,000 or 3,000 PSI. Port fuel injection under 50 or 60 PSI, yeah, it'll hit you in the eye and it'll hurt, but it's not going to poke your eye out. 2,000 PSI will cut your finger. So imagine getting hit in the face with that. It's not going to feel good, and you can end up in the hospital. So how do you bleed the pressure off of this system? It's pretty simple. Remove the relay for the lift pump, start the car, and let it stall. It's the same way we remove pressure on a port fuel system. Once that injection pump runs out of lift pressure, the injectors will spray out the remaining pressure inside the rail. Now, there are bleed-off procedures. Follow them. Look them up with manufacturer service information and follow what the manufacturer says to do. But in a nutshell, it's basically going to tell you to disable the lift pump to the injection pump, so that way the fuel is just not there anymore, and whatever fuel is in the rail, when the injectors are opening and closing, it'll bleed off that pressure naturally, just by itself. If you remove and disturb these injectors and the seals, there's copper seals, there's like a crush seal, or some sort of fuel rail. Long story short, these fuel system components, once you open them up, you must replace them. You can't reuse a crush sleeve type fitting on any of these systems. So if you get in there to remove an injector and replace it, service information is probably going to tell you to also replace a fuel rail. And so that's another reason why these get more expensive, is because a lot of these parts are one-time use. It's kind of like a flare fitting on a normal fuel line, except for once it crushes down, that becomes the seal, and you can't be sure that it'll completely seal back up again a second time. So you have to discard all of those seal components, those hard metal or copper pieces that create the seal around the injectors and the fuel rails. They're disposable. And that's true with diesel stuff too. If you're working on a diesel engine, you're technically supposed to dispose of a lot of that stuff. A lot of people don't, and they get away with it, but keeping in mind, if you've got a 2,000 or 3,000 PSI leak, you may not see it depending on how bad it is. You might have just a little odor coming from that leak, and you run the potential of having a fire under the engine bay because you didn't replace something. So you don't want that to come back on you as a technician. Trying to think if there's anything else in here. This chapter is relatively short. So I'm going to go ahead and end it there. If you have any follow-up questions, get a hold of me. Watch the videos that I have online on YouTube. There's a couple of videos there that are really good at explaining the components and the cleaning process and diagnostic processes. So I hope you got something out of that, and get a hold of me if you have any further questions.